Working with microbit. In this lesson, we'll introduce you to the microbit, a small programmable device. We will explore its schematic view, identify its key components, and learn how to control its LED matrix. We will also delve into the use of its motion sensors, buttons, light, and temperature sensors. Furthermore, we will learn how to connect external components to the microbit and utilize a breadboard for more complex projects. Introduction to microbit. The microbit is a microcontroller board based on ARM Cortex-M processor cores licensed by ARM Holdings and used for learning purposes mainly in the UK. The microbit has 25 external connections on the edge connector of the board, which are referred to as pins. The edge connector is the gold area on the right side of board. The diagram shows the functions and the arrangement of the pins on the board. You can view the microbit schematic here. Microbit parts. ARM Cortex-M processor cores. The brain of your microbit. Micro USB port. Used for powering your microbit, uploading your sketches, programs, to your microbit, and for communicating with your microbit sketch. 2 buttons. 2 programmable buttons, A and B. G&D and 3V pins. Use these pins to provide plus 3V power and 0V ground to your circuits. Digital/analog pins. Interpret binary data, on or off, from an input component like a switch, or interpret a range of signals from an input component. 25 LEDs. 25 LEDs output in 5x5 matrix built into your microbit. You can view microbit stator kit here with various input and output components. Lighting up the microbit LED matrix. This activity displays 2 different LED patterns on start with a delay of 1 second between each pattern. The Show LEDs block is used to display the LED pattern on the microbit. The first pattern displays number 1, while the second pattern displays number 2. The Wait 1 secs block is used to pause the program for 1 second before displaying the next pattern. This activity requires 1 microbit only. You can view the microbit schematic here for quick reference. Open Components panel and drag a microbit microcontroller to your workplane. To lighting up the microbit LED matrix, click Code button to open Code Editor. Your Blocks Editor shows 2 containers at start. On Start, Forever, drag Show LEDs code block from Output, Category, and drop inside on Start container. Its squares correspond to the LEDs on the front of the microbit. Click its squares to make a number, such as 1. Add Wait code block from Control Category, and then add Show LEDs code block from Output Category, and click its squares to make another number, such as 2. Start simulation. You can view the block code and equivalent Python code here. Microbit motion sensor and buttons. This activity demonstrates how to use the microbit's LED matrix and random number generator to simulate rolling a 6-sided die. It generates a random number between 1 and 6 and displays the corresponding LED pattern on the matrix. The LED patterns represent the dots on each face of the die, allowing the user to visualize the result of their roll. Meanwhile, button A has been programmed to turn off all the LEDs. This activity requires 1 microbit only. You can view the microbit schematic here for quick reference. Open Components panel and drag a microbit microcontroller to your workplane. To develop a block program, please follow the steps outlined below. Click the Code button to open the Code Editor. Select Basic Category, then drag the OnShake code block to the Blocks Editor. Select Output Category, then drag the Clear Screen code block inside the OnShake code block. Select Variables Category, then create variable named as number and click OK. Then drag Set Number to 0 code block under the Clear Screen code block. Select Math Category, then drag Pick Random 1 to 6 code block in the Set Number to 0 code block, i.e. Set Number to Pick Random 1 to 6. Select Control Category, then drag If True, then code block under Set Number to Pick Random 1 to 6 code block. Select Math Category, then drag the comparison operator. Number sad face 1, code block in If True, then code block, i.e. if number sad face 1, then select Output Category, then drag Show LEDs code block inside If number sad face 1. Then duplicate the if number sad face 1. Then container 5 times. Next, update the numerical values in each comparison to correspond to a number between 1 and 6, and map the number value of each statement to the respective LED you wish to light up using the Show LEDs code block. Select Basic Category, then drag on button, pressed code block on a new spot at Blocks Editor. Select Output Category, then drag the clear screen code block inside drag on button, a pressed code block. Click Start Simulation to test your code. Press the button to turn off all the LEDs. You can view the block code and equivalent Python code here. Light and temperature sensors on microbit. The activity is designed to continuously plot a bar graph of the current light level up to a maximum value of 255 using the micro-bits LED matrix. The graph will update in real time as the light level changes. Apart from that, when the Veil button is pressed, the code will display the current temperature in Celsius on the micro-bits LED matrix. Overall, this code provides a simple and useful way to monitor the light level and temperature using the micro-bits built-in sensors. This activity requires 1 micro-bit only. You can view the microbit schematic here for quick reference. Open Components panel and drag 2 microbit microcontrollers to your work plane. To develop a block program, please follow the steps outlined below. Click the Code button to open the code editor. Select 1 microbit. Select Basic Category. Then drag the plot bar graph of 0 up to 0 code block to the forever container. Select Input Category. Then drag the light level code block to the first 0 spot and then type 225 in the second 0 spot, i.e., plot bar graph of light level up to 255. Select 2 microbit. Select Basic Category. Then drag the 1 button, pressed code block to the code editor. Select Output Category. Then drag the show number 0 into the 1 button pressed container. Select Input Category. Then drag the temperature, degrees C, code block to the 0 spot, i.e., show number temperature, degrees C. Click Start Simulation to test your code. Drag the light intensity slider up and down on the microbit to see the LED change based on the amount of light. Press the button to have the temperature display on the screen. You can view the block code and equivalent Python code here. Using microbit with external components. In this activity, code continuously reads the analog input from pin P0 and plots a bar graph on the micro-bit display that represents the input level from 0 to 1023. Additionally, it writes the same input level to both pins P1 and P2 using the write analog pin block, which sets the voltage level on those pins to the corresponding analog value read from pin P0. Overall, this code provides a simple example of how to read and output analog signals on the microbit. This circuit requires 1 microbit, a hobby gear motor, NPN transistor, a 1K omega resistor, and an LED. This schematic illustrates a circuit incorporating a microbit, a 250K omega potentiometer, a hobby gear motor, 3 AA batteries, not 1.5V, an NPN transistor, BJT, a 1K omega resistor, and an LED. The microbit is connected to the potentiometer, which controls the motor's speed. The NPN transistor acts as a switch, allowing the microbit to control the motor's power. The LED provides visual feedback, indicating the motor's state. To develop the electronic circuit, please follow the steps outlined below. Open Components panel. Select and drag 1 microbit microcontroller, 1 potentiometer, 1 LED, and 1 hobby motor to the workplane. Also drag 1 battery pack, 1 resistor, and 1 NPN transistor to the workplane. These are required because a motor can draw more power than the USB port is used to providing. Rotate the potentiometer, LED, NPN transistor, and hobby motor using R and drag it under the microbit. Connect the potentiometer to the microbit by wiring the center pin to pin 0, the right pin to 3V, and the left pin to GND. Connect the LED to microbit by wiring the anode, longer leg, to pin 2 and the cathode, shorter leg, to GND. Connect the NPN transistor to microbit by wiring the transistor's base to pin 1 using a 1K resistor. Connect the positive end of hobby motor to the transistor's emitter and the negative end to the GND on the microbit. Connect the battery pack's positive terminal to the transistor's collector and its negative terminal to the GND on the microbit. To develop the block program, please follow the steps outlined below. Click the Code button to open the code editor. Select Basic Category, then drag the plot bar graph of 0 up to 0 code block to the Forever container. Select Input Category, then drag the Read Analog pin P0 code block to the first 0 spot, and then type 1023 in the second 0 spot, i.e., plot bar graph of Read Analog pin P0 up to 1023. Select Output Category, then drag the Write Analog pin P1 to 0 code block to the Forever container. Select Input Category, then drag the Read Analog pin P0 code block to the 0 spot, i.e., Write Analog pin P1 to Read Analog pin P0. Select Output Category, then drag the Write Analog pin P2 to 0 code block to the Forever container. Select Input Category, then drag the Read Analog pin P0 code block to the 0 spot, i.e., Write Analog pin P2 to Read Analog pin P0. Click Start Simulation to test your code. Rotate the knob of potentiometer connected to P0 on the microbit to see the bar graph update, along with LED light based on the sensor reading. You can view the block code and equivalent Python code here. Using a microbit with a breadboard. This activity uses a forever loop that toggles the digital output pin P1. It does this by repeatedly setting the pin to high, waiting for 400 milliseconds, setting the pin to low, and waiting for another 400 milliseconds before starting over again. This code can be used to drive a simple LED blink circuit or any other circuit that requires a periodic digital signal. This circuit requires one microbit, an LED, and a resistor. You can view the schematic here, where P0 is connected with a resistor and an LED in series. There's a limit to the number of components you can easily add via direct wiring to microbit. You can expand the capabilities of your microbit circuits by adding a breadboard, which creates more room for prototyping. To develop an electronic circuit, please follow the steps outlined below. Click and drag the microbit and the breadboard small from the library onto the workspace. Place the breadboard below the microbit. If you want to rotate the breadboard, select it and press R on your keyboard. The breadboard component has power rails and terminal strips. The power rails on each side of the breadboard are electrically connected, positive, plus symbol, and negative, minus symbol. Each row of terminal strips is electrically connected. 2. Create a wire connection from pin 1 P1 on the microbit to a red positive, plus symbol, power rail on the breadboard. Select the resistor from the library and place it across the central valley of the breadboard, connecting the two terminal strips. Click the resistor. In the pop-up, change the resistance value to 470 and choose Ohm from the drop-down menu. To develop a block program, please follow the steps outlined below. Click the Code button to open the code editor. Select Output Category, then drag the digital write pin P1 to high code block to the Forever container. Select Control Category, then drag the wait 400 milliseconds code block to the Forever container. Select Output Category, then drag the digital write pin P1 to low code block to the Forever container. Select Control Category, then drag the wait 400 milliseconds code block to the Forever container. Click Start Simulation to test your code to see your LED flash. You can view the block code and equivalent Python code here.